Hi, my name's Kevin Crimi. I spent my time with OSDC in Tsukuba, Japan at AIST working with the Media Interaction Group, led by Dr. Goto and working personally with Dr. Hamasaki. My time there was spent mainly working on visualization techniques for highly dimensional data, namely music collections. And I'm going to go over some of the techniques that I worked on while I was there. This is a web app that was developed by the lab, and it's called Songrium. It is a collection of videos online that are hosted on a Japanese, so you can think of it as similar to YouTube, but it has mostly animated videos for songs, and you can post your own, and this web app lets you link them together and list them as similar artists, similar moods, that your video is a cover song of a different original video. So it provides a real interactive social environment for this music listening. My time was actually spent on YouTube videos, so unlike the Nico Nico data, I was actually using YouTube music videos, and each of these little over 10,000 videos had a 63-dimensional feature set, which was a result of timbral analysis done to the audio, giving MFCC, I'm not going to go into what they are, but features which represent the timbral information of the music. And my job was to try to visualize this in a two-dimensional space. This technique that I found that was very promising was called stochastic neighbor embedding. You can see its result is the top left. On the bottom right is the traditional principal components analysis. And while the PCA does have some clusters, you can see the red and the orange, and there are clusters there. It is not as distinct as the stochastic neighbor embedding, which retains both the local structure, so each of these classes is very nicely clustered together, but it also retains the global structure. So this was actually handwritten digits, so each of these colors pertains to a different number, 0 through 9, and this light green over on the right is 1, under it is fuchsia was 7, and the blue under that was 9. So you can see that even similar digits are starting to cluster together, so it retains both the local and global structure, which is something we really wanted for that mapping, to get a songs in a similar pattern to that star pattern I showed you before for song. Now, this is the technique that I use, parametric TSNE. You can see there's some little additions onto the name of it. So stochastic neighbor embedding usually uses Gaussian. This uses a t-distribution. So what does that mean? The way this technique works is it converts the distances, Euclidean distances, of the highly dimensional points and the low dimensional points to probabilities. You can think of this as the probability that one point will actually choose another point as its neighbor. And when you're dealing with the Gaussian, you can have a tendency to sort of cluster and crowd the points together. I was using the variation of using t-distributions, which can get around that problem. In addition to that, I use the parametric version, which a lot of the problems with this the mapping techniques out there is once you map your data, you can't really add any more data to it. So you have this really nice mapping. However, we're using YouTube videos, so we want to constantly be adding to that. If we have 100 more songs, now we have to rerun the mapping on our whole library once again, which can be annoying computationally and for the user side. When your videos are constantly moving around, you can't really get a feel for where you are in this spatial environment of videos. So what we wanted to do was use the parametric version, and this is done by using a neural network to produce this mapping. The way this works is we have a 3-layer neural network. So in this case, we would take the voxels of this handwritten digit, feed it into one layer, that'll go into another layer, and another, and then finally into a layer with only 2 nodes, which would represent our x and y axes. So basically getting it down from the feature space of each point to a 2-dimensional space so we can actually map them. Now, each one of these layers, the connections between them can be thought of as a restricted Boltzmann machine. This is just an undirected graph, which every node is connected to the other in the other layer. And we wanted to train each of those RBMs first, and then you can combine them for a full neural network. Once you do that, then you can use this cost function, don't worry about it, to fine-tune the whole neural network. And this is essentially just reducing the differences between the probability seen in the highly dimensional space and the probability seen in the low dimensional space. So you're trying to minimize that as much as possible, so high probability points that would choose each other are equally high in the low dimensional space as they are in the original space. Now I'm going to show some of the application to my feature set. You'll notice it's just one color. Unfortunately, there are no genre tags in this music, so without that metadata, I can't really visualize a nice clustering algorithm, which is a problem when that's what I was working on, right? So what I decided to do, I handpicked some very distinctly different artists and to see if they would cluster away from each other. Unfortunately, as you can see, this is Lady Antebellum, kind of all over the entire mass of points. Then Mariah Carey. Then Rolling Stones, very different from both of those, yet still all over. And T.I., even more different, and still all over this. So, and this is just another mapping of the 100 top artists and their centers, which you can see is mainly in the center of the mass of points, which means it's probably uniformly distributed, which is a problem when you're trying to cluster them. So what I did is I went to this, once again, lovely clustering of the MNIST handwritten data set and tried to destroy it to emulate similar problems. Now, when I cut it down to the same number of songs as us, it still retained its clustering capabilities. Now, when I injected noise into 10% of it, you can see a lot of the noise in the top. You can start to see some problems popping up, and this is only 10% of the data. Now, we're using 10,000 songs, that's only 1,000 songs, which if we have just interviews, because this is YouTube now, it's not very regulated. Now, if we have interviews instead of music videos, that's noise in our data that can definitely hurt our clustering capabilities. And worse, when we cut the dimensions down to 63, which is our dimensionality of our YouTube data, it just collapses in on itself and demolishes our mapping. So this is really promising on some of the problems that we have with this algorithm. So it seems this algorithm is very sensitive to the dimensionality. It likes high dimensional data, which we're trying to remedy when I was leaving. So this is sort of what I was working on as I left the program. We have new analysis techniques that would have higher dimensions, trying to cross-reference the CDDB database, which is unfortunately very noisy, to get some genre tags to these songs. We're testing pre-processing techniques such as auto-encoders and data whitening up front to try to get cleaner mappings. And then finally, I was just putting out some feelers into other techniques, which on the right here you can see this is called the tree-preserving embedding, which although it doesn't have tight clusters, it does have a nice even distribution, which they thought might be usable and might be more beneficial in a user interface. So this is some of the stuff that I left them with when I left, and now they're continuing to try to figure out what is the best way to map these songs. All right, I'm sorry I'm a little over time, but thank you very much for your time.